Hello, I am Samy Castro and thank you for attending my virtual poster. Brain regions communicate through oscillations. It has been shown using spectral granular causality that top-down and bottom-up influence explode respectively slower or faster frequencies. This raises several questions. How is this frequency diversity and specificity generated? And more speculatively, why, for which real purpose, should communication be frequency specific? Let's start with the first question. Explanations have been advanced in terms of structural features. The cortex is multi-layered with a specific canonic wiring. In particular, cortical feed-forward and feedback connections have different source and target layers. Also, this source layer presents different layer-specific frequency of oscillation. For the superficial layer, fast frequencies, and for the deep layer, slow frequencies. This matches the frequencies of outgoing functional connectivity. This property is usually explained by invoking different layer-specific abundance of spike pulsar booming and somatostatin interneuron, having different resonance frequencies. However, if frequency-specific communication is generated by hardwired structural features, how could it be flexibly modified? In order to answer these questions, we use modeling. We use a layer beam field model of the canonical cortical circuit with a realistic multi-layer connector. Equations include just one excitatory and one inhibitory population per cortical layer. All inhibitory populations are identical on the phase spike in type. In addition, we have tunable current terms targeting different layers whose increase emulated increased stimulus latency or boosted attention. Modulated these currents in modified contextual input without changing the circuit. This gamma corresponds to the relative strength of different AA, AI, IA, and II connections coming from experiments. However, the absolute strength of excitatory and inhibitory connections are free parameters, and we can obtain different dynamical regions by changing them as shown in the following phase diagram. In particular, we find different oscillatory regimes. In the yellow region, oscillations are dominated by fast frequency in both superficial and deep layers. If we increase excitation, we enter this blue region in which the superficial layers are fast, but deep layers oscillate now at a slower frequency. Please note that this frequency separation is now emerging from network interactions, as there is no interneural diversity in the model. In the same zone, we also compute spectral granular causality. In this diagram, red or blue colors means communication arises respectively at slower or faster frequencies. Focusing on this working point, one finds as a free lunch the same association between the direction of communication and frequency as in empirical data. As just mentioned, this frequency specificity is a property emergent from dynamic. Therefore, it can be changed by changing dynamics. For instance, we show here how by changing the attentional gain, we can turn the frequency of top-down functional connectivity from slow to fast frequency or vice versa. Thus, flexible frequency of communication can exist despite the same connectivity structure, down to dynamic complexity. Layer-specific multi-frequency communication emerges from self-organized collective dynamic, and thus this communication is flexible and not hardwired. So, do we really need such a specific interlayer wiring? After all, similar dynamic might arise in different circuits. To assess the cortical circuit, we randomized interlayer cortical connection generated 100,000 surrogate networks. Surprisingly, we found that only a tiny fraction of the tested connectons led to the emergence of layer-specific frequencies. Yet, all of them are different from each other structurally and not forming a cluster. Despite some shared overrepresented motifs, what do these multiple good connectons have them in common? Selecting one of them is comparable to finding a needle in a haystack. This task can become easier if we search for some target feature. Our hypothesis is that these connectons are optimal in an information theoretical sense, in the sense that they make possible special types of information processing. Following Tononi, Edelman, and Sporns, efficient brain functions relate on the coexistence of segregated and integrated information processing, called complexity. Here, to study the style of processing in the dynamic of different connectons, we used two information metrics, introduced by Rosas, Mediano, and Jansen, the so-called S-information and O-information. When the S-info is large, complexity in the set of Tononi et al. Is also large. Furthermore, when O-info gets negative, it indicates the existence of a large number of high-order synergies. Here we show how this S-info and O-info depend on the dynamical regime for our empirical connector. At working point, the system is dominated by synergies. This working point also maximizes S-info, or equivalently, complexity. Coming back to the randomized connector, in the good shuffled connector, the slow-fast working point maximizes synergies and complexity. None of the bad connectors can achieve such optimization of synergies and complexity. In conclusion, frequency-specific cortico-cortical communication may have a dynamic rather than a structural origin, even if only special canonical variants can optimize synergy and complexity. As a speculation, we are: is frequency-specific of communication as an algorithmic expander? Expanders are the space that emerge when an arc is constructed in a rectangular frame. Conceptually, this expander opens new possibilities, not necessarily at the beginning, as this beautiful painting in Donald Church. Sometimes they can become unexpectedly useful by themselves, as in this futuristic building where spandrels are filled with photovoltaic panels. Thank you for your attention. Feel free to contact us for questions and discussion, and this is our poster information.